put your link, so hopefully you're happy to continue. So please do so.
Thank you very much for that introduction. Apologies that I can't be there in person. I'm going to be talking Ptychography, which is a form of computational imaging. I'm not sure how much application it's going to have in XFEL, which it should be, they don't know much about. But it may be helpful to point out some of its capabilities, and perhaps people will have ideas of how they may be able to apply it in that context. So what is the name was intended to imply a form of pathology or a way of recovering the phase of waving. And it has two components. We have to have an intermixture of wave interference, and that intermixture is folding, tycho means to fold, and translation diversity, which is shifting, which I'll explain over. So this is the basic principle. We have a statistic here. We have an illumination function. We record a diffraction pattern in intensity. We then move the specimen or the product of illumination, and we record another intensity pattern. And then we scan it across the whole sample, which will create a four-dimensional data set of illumination positions and diffraction patterns. Now, there's no obvious reason why we should be able to solve the object, because we have the phase plot. In other words, we can only measure our diffraction patterns in intensity, and we keep the phase. However, we can. And once we can, this method is applicable to any propagating waves. Now, there's a number of solution methods that I'm not going to describe in detail. Suffice to say, they are now well established, and I just don't have to talk about how we solve for the phase. However, for microscopy, which is my interest, the benefits of topography are many. First, record then recover an image phase with near perfect transfer function. So let's break X-ray, EV, or electron microscopy, which are largely limited by lenses. It's ideal for tomography. Furthermore, we can calibrate the optical system, couples the object and the illumination function. Here, I note the typography, just a shifting function with respect to a number. So we can solve for the illumination function of the object function. Now, in electron, there's various other benefits, like needing to source instability. You get a very strong fade image with low counts. And we have a lot of redundancy in the data, diversity, which means we can remove free people scattering and experimental errors. Furthermore, we can pull out, get a mixed state. So the object may more than one state, but we can pull it down. I've just highlighted red, might be relevant in context. Right, so in an optical microscope, you might see looking at what look at some cell, but you do get a different pattern. And biological in this case, you illuminate area, and then you get a series of patterns. And this redundancy in the overlap leads to the solution of vector problems. Now, there's lots of ways of solving this, but this is just an example of it's the first illustration of a solution to this phase problem. And here we're getting the image out on the left in absorption. Sorry, let's stop that too. On the left in absorption, on the right in phase. And at the end of this calculation, you get a modulus and phase addition. Nowadays, you can get very, very high quality phase, for instance, of unstained cell felt. This is one of its major applications. And this is also true for X-rays. However, you can't easily arrange for a systematic scattering process sample using an XFX together. There are opportunities, I think. One is if we have a crystalline object, or indeed we manufacture an object with a period system, with some object of interest within it, then even if we can't scan systematically visible exposure, we will co-pay, and if we illuminate their positions, these will only be displaced to units with the unit cell by a small amount. And we know that in conventional typography, we can refine our knowledge of the illumination positions, which in this case is green dots, with our guesses of the illumination position, or we think they are. And if we run this calculation, you can see that during the process, we actually solve for the probe position. So that's a possibility. Even if we're not in control of the beam very accurately or accurately at all, still use the typographic principle to get an image out. One thing is this characterization of the probe. This has already been done. I think this was done in quite a few years ago. And this is at Ptychography. You're probably all familiar with this, but here is a test sample. They had a periodic test sample. And this is the illumination function that they solve for. Once you solve the illumination function, it's in complex amplitude, so you can back propagate it. And whoops, sorry about that. And find out what the beam crossover looks like. So in other words, you can characterize your optics. And I think that's the major application. Notice that this, I'm going to keep on, I'm having trouble with that. That on this scale, the horizontal direction is 5 millimeters, and the vertical and lateral is 5 microns. So this is a very long, stretched out probe. And you can look at individual probes here at the top left, and an average probe, work out the accuracy, the impulse response, if you like, of the probe. The other thing you can do, now take off, is look at the state of mixtures, and this might be important. Just a demonstration that we did, we call this typographic multiplexing, where we have 3 illumination functions, all at different wavelengths, blue, red, and green. The diffraction patterns add up everything being scattered by the object. But we've arranged the object to be, this is an artificial, 3 images, each of a different colour. And if we then do our reconstruction method, now I don't have time to go into this, but essentially, when we measure an intensity at a pixel, we have one measurement. We know that that is being made up of 3 colours, but we don't know the intensity or these phases. Now it turns out we can solve them because we have an estimate and we scale this, we measure, and with all the redundancy in the data, we can separate out these separate nodes. And in this case, actually, the eyes don't really match with the laser. These things come with that. Now, this could have application, very high frequency effects. So, and when I say high frequency, this could be attoseconds. This is a very simple experiment. It demonstrates this, where you have 2 states on an SLM, it's an optical test. You have 2 states in the system, and they flash states at very big frequency. Once you do the separation modes, we can see these 2 modes come out superimposed here for reasons I don't want to go into this to do with an ambiguity in the reconstruction. But we can get around that ambiguity in certain circumstances and thereby pick out the 2 modes. So what would that mean? If we went back to our original experiment, this could be an oscillating, it could be the electron cloud oscillating at very, very high frequencies, but the modes could be drawn out even though our detector is detecting over relatively very long periods of time, a fraction of a second. So, I think that's it.
Okay, so shall we any questions for John? Questions? Okay, I'll ask a quick question. So you just briefly went over this idea of modes and attoseconds, timing possibly. Can you just say a bit more about that?
Yes, so when we collect our data, the diffraction is made up of 2 objects, scattering, and then those either integrate in the detector. So the detector cannot possibly separate out 2 states because it integrates those 2 patterns over a very long time. However, because of the constraints of ptychographic data relating to the illumination function and its relative position, there's only 2 functions that can give rise to those diffraction patterns, or that single diffraction pattern. You see what I mean? So the 2 functions can be separated out, even though we've only recorded 1 diffraction pattern over a long period of time.
Okay. Yes.
So, I don't know if you can hear that. The question was, so what is being shown, so essentially are images that are taken just with 1 channel in intensity. Can you mention or discuss the possibility of doing dichroic images, for example?
Okay, so we have a question.
Or minor images.
Sure, we have a question about doing dichroic images, creating dichroic images for magnetic measurements. Is this possible?
That has been done. That's being done. I haven't put in images of that, but it's being done, I think, Well, is it now? If anyone's interested, I haven't done it, that has been done.
Okay, so maybe we can send you an email if you want to know more. Okay, question there.
Also on this time resolve or getting the two images from a filtration, is there any good continuous transition between the two? Would you be able to resolve this image, or it has to be two discrete states that last for a finite lifetime?
Okay, so the question is, if
I did hear it, I think I heard this. We've done it here with two discrete images. In principle, you can separate out many of these modes. So, I don't know what records they've been looking into how many modes we can separate out. It's of the order of tens or more. So in principle, if we had something that was going through a continuing motion, it may be possible to pick out a movie. But we know that we've attempted that.
any other questions? Okay, let's thank the speaker again.